Welcome to this explainer. Let's jump right in, because today we're completely transforming how we think about teaching decimals and percents. For decades, instruction has kind of relied on memorizing these rote rules, right? Things like move the decimal 2 places to the left, or just line up the dots. But what if we completely abandon those fragile little tricks and built a deep, unshakable conceptual understanding instead? Well, that's exactly what we're going to unpack today. We're going to focus specifically on highly effective instructional strategies for developing these foundational concepts in grades 3 through 5.
So think about this question for a second. Is there ever a smallest piece in math? When we're teaching young learners, that single unit or ones block, it kind of seems like the absolute bottom of the barrel. But I want you to imagine our base 10 system extending infinitely into smaller and smaller pieces. Imagine a block divided into 10 strips, then those strips into 10 tiny squares, those squares into 10 microscopic slivers, and so on, literally forever. It absolutely challenges our own adult intuition. But understanding this infinite, two-way street, that is the absolute bedrock of decimal comprehension.
Okay, let's look at our roadmap for today, which actually mirrors the exact developmental progression students must take to truly master these concepts. We're going to start with 1. Extending the base 10 system. Then 2. The decimal points role. 3. Visualizing decimals and fractions. 4. Overcoming common decimal misconceptions. 5. Mastering decimal computation. And finally, 6. Introducing percents as hundredths. Let's dive in.
Section 1. Extending the base 10 system.
We really need to shift from thinking about place value as just, building up to thousands and millions. We have to understand that this 10-to-1 multiplicative relationship works seamlessly in both directions. Now, this is a massive paradigm shift. A lot of adults, and consequently the students we teach, believe the number system is symmetrical around the decimal point. No way, it's not. The base 10 system is fundamentally symmetric around the ones place. So to the left of the ones, we have tens. To the right of the ones, we have tenths. Hundreds on the left, hundreds on the right. The ones place is the actual center of our base 10 universe. Grasping this structural symmetry is a total game changer for kids.
Section 2. The decimal points role.
So if the ones place is the true center of symmetry, what exactly is the purpose of that tiny, often misunderstood dot? Well, here is the absolute crucial point. The role of the decimal point is to designate the unit's position, and it does so by sitting just to the right of that position. That's its entire job. It's literally just a convention. We could choose any base 10 block to be our unit or our 1. The decimal point is really just a little visual marker, telling everyone looking at the number, hey, the position to my left, that's the unit we're counting by right now.
And this brilliantly illustrates that idea. Think of the decimal point as having a little pair of eyes looking up and to the left. It always looks up at the name of the unit's position. If you have a collection of base 10 materials on the desk, like superstrips, squares, and tinies, you can actually change the designated unit without changing the physical quantity at all. If a square is the unit, the dot goes after the squares. If you decide a strip becomes the new unit, the dot simply shifts to sit right to the right of the strips. It is such a powerful visual trick, and it entirely removes the mystery of the decimal.
Section 3. Visualizing decimals and fractions.
Okay, so once students finally grasp what the decimal point is actually doing, we absolutely must ground these abstract symbols in concrete visual models. And we have to do this before we ever touch an algorithm. For a lot of students, fractions and decimals feel like two completely disconnected mathematical worlds. We have to explicitly bridge that gap. The source material highlights two incredibly effective visual proofs: the rational number wheel with 100 equal intervals and the classic 10 by 10 grid. By physically shading these models, students can literally see that 3/4 takes up the exact same physical space as 75/100. Creating this concrete visual connection is completely mandatory before we start teaching any operational rules.
Building true number sense means developing a deep intuition for relative size. We do this by connecting decimals to fractions kids already know and using basic benchmarks, 0, 1/2, and 1. For example, ask your students, is 7.3962 closer to 7, 7.5, or 8? Well, if they know 0.39 is roughly 0.4, which they know is less than a half, they can confidently say, oh, it's closer to 7.5 than to 8, but ultimately closest to 7.4. This is exactly the kind of flexible thinking we want to cultivate.
Section 4. Overcoming common decimal misconceptions.
Now, as students start exploring decimals, their past success with whole numbers is actually going to betray them. They face some very predictable roadblocks. Kids learn early on that a 3-digit whole number is always bigger than a 2-digit one, right? So they wrongly assume that 0.375 is greater than 0.97 because, in their minds, longer is larger. Or they might ignore the internal zero entirely and think 0.58 is less than 0.078 because 58 is less than 78. On the flip side, some overcorrect. They think shorter is larger, reasoning that a tenth is bigger than a hundredth, so 0.4 must be larger than 0.97. Adult intuition often glosses right over these pitfalls. We completely forget how confusing this was for us. The fix? Pull out those 10 by 10 grids and decimal cards. Have them physically build the quantities and compare the shaded areas.
Now, what's really fascinating here is seeing these exact misconceptions play out on paper. Notice these student attempts to place 0.7 and 0.07 on a number line. Without a firm conceptual grasp, their spacing and ordering are completely skewed. Some place 0.07 way further to the right because they're heavily focused on the whole number 7, or they're honestly just randomly guessing the intervals. Empty number lines are incredible diagnostic tools. They instantly reveal what students truly believe about magnitude and scale.
Section 5. Mastering decimal computation. So once place value and magnitude are completely secure, we shift to operations. But standard algorithm should absolutely be the final step, not the first. And if you need proof of why, consider this NAEP exam data. On the National Assessment of Educational Progress, only 29% of high school students could correctly translate 0.029 into the fraction 29 over 1,000. That means 71% got it incorrect. Wow! When we force kids to just line up the dots without understanding why they're doing it, the knowledge evaporates. They memorize a procedure to pass a test, and they completely lose the mathematical meaning. So, how do we fix this? We follow this mandatory instructional scaffolding. Step 1, always start with estimation. Before a pencil ever touches paper to line up a decimal point, students must predict a reasonable answer using whole numbers. Step 2, encourage invented strategies using those visual models we talked about to calculate the exact answer. And finally, step 3, only after steps 1 and 2 are rock solid do we formally introduce the standard algorithm. The core logic of decimal computation is simply an extension of whole numbers. It's exactly the same underlying concept. You are adding and subtracting numbers in like position values. You add tenths to tenths and hundredths to hundredths, just like you add tens to tens and ones to ones. Once place value is truly understood conceptually, the mystery of decimal computation completely vanishes.
Section 6. Introducing percent as hundredths.
Now for our final piece of the puzzle. Percent is literally another name for hundredths. That's the whole shebang. Remember how we said earlier that the decimal point designates the unit? Well, if you decide that the hundredths position is going to be your unit, then the word percent is simply a synonym for that unit. If you have 65 hundredths, you have 65%. There are no confusing rules about jumping the decimal point 2 spaces left or right. It's essentially just a vocabulary change.
And this is where it all comes together so beautifully. 3/5 is mathematically equivalent to 60 hundredths. On a 10 by 10 grid, you'd shade 60 little squares. Written as a decimal fraction, that's 0.60. And because percent means hundredths, that is seamlessly 60%. A single 10 by 10 grid unifies fractions, decimals, and percents in one comprehensive visual model. This visual flexibility with grids, or even using simple bar models to solve percent problems in real-world contexts, completely bypasses those mechanical rules we all grew up with. We have covered a massive amount of ground today, transitioning from rigid rules to a rich visual understanding. So I want to leave you with this final provocative thought to mull over. Are you ready to finally ditch the memorization rules and teach decimals conceptually? Your students are capable of profound, flexible mathematical thinking when we step back and give them the right visual tools. Thanks for joining me for this explainer, and I'll see you next time.